We took our limit of delta r as it goes to 0. We know 1 over r does not equal 0. And so if we take the limit of this function as it goes to 0, we get negative ddr tau r equals to 0. We need to find something to replace this tau with. So we need to identify what tau we're looking at here, right? We have tau ij. Tau ij. This is going to be the plane we're shearing and the direction of shear, I and j. So we're shearing then a radial plane, looking at this image in this free body diagram here. We're going to be shearing a radial plane, and we shear that radial plane in the direction of z. So our tau ij is tau r z. That's important for us because now we need to get out our transport textbook, revisit chapter 2 where we learned about these flux laws. And in table 2.4, we have flux gradient relationships in curvilinear coordinates. And let's see, we have shear on the theta plane in the direction of z, shear on the r plane in the direction of theta. What we just found is we're shearing the r plane. Better for us. That's about it because we're zoomed in here. So we're shearing the r plane in the direction of z, and so our law that we need to replace here is mu dvz dr plus dvr dz. If we consider the expected velocity profile here, we don't have radial velocity, vr. So the change in the radial velocity with respect to z is 0. And what we can replace tau with is negative mu dvz dr. All right, so tau is negative mu dvz dr. Oops, this was shear on a radial plane in the direction of z. We reduced it without a radial component of velocity. Is dvz dr. Could we have done... yeah, so we could have. So, except this is exactly why I didn't want to. So you're kind of seeing now, once we go into curvilinear coordinates, we start introducing more and more radial components. In fact, we'll take a break here from the video. I'm not going to put this up, but to answer your question, yes. The other thing that I mentioned last time was if we're shearing the radial plane in theta, rather than in z, it becomes even more, what I didn't say, I think I didn't articulate well, is it's even more nonlinear. And so if we were already introducing a function for tau, I didn't want to start playing around with introducing functions for tau plus introducing multiple curvilinear coordinates. But let's take a look at tau r theta, because now you see this is even worse. Right? We were left with what we expected, mu du dr, basically, mu du dy. Right? That's what we've seen before, so we're comfortable with. If we go to r theta, now we want to replace mu r ddr v theta over r plus 1 over r dvz d theta. So I kind of skirted this issue when you asked, but what I should have done was bring out the book and shown you these two equations. And then you could have gotten a little better sense, I think, of what I was talking about when I said that this will work kind of if we're working along this z velocity, but it won't really work if we're working in a radial shear. So tau r theta is when the inner rod is spinning. Could be either. So that's a really good question. I'm glad you're asking, because we're getting into radial systems for sure. Next example we're going to do is also a pipe. We're going to be working with pipes a lot. So anytime that we expect to shear r theta, yes, is when inner rod, but I guess, yes, correct. So the question is, so tau r theta when the inner rod is spinning or the outer rod. The inner rod can be stationary and the outer rod can spin. But what we're looking at then is if we have our annular ring, are we twisting this around? Is the shear in theta, right? Are we shearing this around the axis in theta? Or are we shearing this back and forth? And that gives us the second indice, right? We know we're shearing the R plane, but whether we're shearing around in theta or whether we're shearing in Z changes this to be tau r Z or tau r theta. So it's correct in what you said, but I want to just make a point that inner rod, outer rod, as long as if it's a whirlpool, we could apply tau r theta. So anytime we have rotational fluid draining down the sink drain, right, we can apply tau r theta to that. If it's the axial thing, it's tau r Z. If it was the two planes, right, we said, all right, we're shearing a y plane in the direction of x, tau yx, and that was mu du dy. And I should actually, if we take a look at that a little more, the reason that was tau is mu du dy is because we have one-dimensional flow. Here's u, vx, dy. Tau is mu du dy. If we had two-dimensional flow, we would have had to include some sort of y component of the velocity. We're in transport 1, so we are not in 2 dimensions yet, and this actually looks exactly like what we saw for the shear law, as long as we're shearing along z. So I think I watched the video and I did not explain that very well. I kind of just said, well, it's up to you. The truth is I still wasn't feeling that well. I was still kind of in recovery mode, so I wasn't quite ready to do some mental acrobatics. But yeah, so that is the answer to your question. So hopefully, excellent. That makes sense? Perfect. Yes, so we introduced one radial component as we are working along in Z. We now have tau r. If we were shearing around in theta, this would become even worse. So we're not even going to do that. We won't shear in theta until we get to transport 2. Then we'll look at how to shear this thing around in theta. All right, so let's get back to the derivation here. We found that we needed to turn to table 2.4 to get this, and you're going to have a take-home exam at this point, so you should be totally comfortable with, I'm going to turn the brightness up here, with going to table 2.4 and looking this up. That should not be a problem since you have taken an exam at this point. All right, so where's my Sharpie? And let's get back to it. So now we need to include the radius, right? So the only thing that's really changed for us is our differential is going to be negative. Oh my goodness. So I don't know what's going on with my Sharpies today. First one was dead. This is just dripping everywhere. All right, always got to be interesting. Oh boy, all right. So let's start here. After we took the limiting process, we found this was going to be negative dr of tau r equal to 0. We looked at table 2.4 and found that tau can be written as negative mu dvz dr. And so we can make that replacement. So tau is going to be replaced in our differential, so we can get a velocity profile, right? We know that this is telling us that the shear times the radius is constant in our system, right? This is equal to 0, the derivative, so this is constant. And we want a velocity profile out of this, so we will replace tau, negative mu, dvz dr, equal to 0. And now we can assume that constant mu, right? We don't have this function. We're just going to pull out we can pull out negative mu actually, let that negative cancel, and we know that mu is not equal to 0. Oop, and we forgot